Today's lesson will give you a chance to practice finding the domain when you look at either the equation of a function or the graph of a function. In yesterday's lesson, we spent quite a bit of time finding the domain when we're given the graph of a function. Today's video will help you dig a little bit deeper into how to find the domain when you're looking at the equation of a function. So before you watch any more, make sure you have today's document open. In this video, I'll guide you through part 1 of the document, which is the first page, and we'll be taking, like I said, a closer look at how we can find domain from the equation of a function. You might want to consider splitting your iPad screen so that you can watch this video and write on the document at the same time. You might also consider using a second device to watch the video so that you can write on your iPad. So if you're not ready yet, go ahead and pause this video, open the document, and then press play once you're ready. So here we go. The first thing we want to consider when we're thinking about domain is whether or not the operations in a given function have restrictions on what can be inputted for x, or if the domain is in fact unrestricted, meaning that we can plug anything we want in for x. So when we say a function has an unrestricted domain, we're saying that the inputs, the x's, can be any real number. X can be any real number. X is an element of the real numbers. But some functions, because of the operations they perform, have restrictions on the domain, meaning there are certain inputs that we just can't use in that equation. So take a minute here and think, when you think back to those parent functions that you worked with the other day, and you might want to have your graphic organizer out so that you can see those tables and graphs. When you look at those parent functions, which of the parent functions have an unrestricted domain? Meaning, which of the parent functions take any x on the entire number line as an input? And go ahead and pause this video while you think about that. And you can press play when you're ready. Okay, so let's see how you did here. There's actually a lot of functions that have unrestricted domains. Any polynomial function, which is by definition a function where x is the base and we see an exponent. Any polynomial function has an unrestricted domain, meaning we can input anything we want. And that would include linear, where x is to the first power, quadratic, where x is to the second power, cubic, where x is to the third power, and even higher powers of x as well. Exponential functions have an unrestricted domain. When x is the exponent, we can input anything we want. We can input a positive, we can input a negative, we can input 0, we can input fractions for that exponent. And what we see on the graph is exponential growth or decay, where the graph goes left and right forever. The absolute value function can input any number. Now the outputs are always positive, but the domain is unrestricted. We can input anything we want. It actually turns out that the cube root function can input anything. So these are some functions that have unrestricted domains. Okay, but there are a few functions that we've explored that have restricted domains. So for the second part here, I want you to focus on the 3 functions that we did not list above: the square root function, the rational function, and the logarithmic function. Okay, and take a minute and think here. And we explored this in yesterday's Desmos activity, so you could always look back at that Desmos activity for more guidance if you want. Why is it that we can't input anything we want into the square root function? What is it that we can input? Why can't we input anything into a rational function? What is it that gets in the way? And why can't we input anything we want into a log function? Instead, what must be true about those inputs? So take a minute and do a little brainstorming here. Pause the video, and when you're ready for some feedback, you can press play once again. Hey, again, let's see how you did. For the square root function, the reason that there's a restriction is because we cannot square root negative numbers. And the reason for that is because square root is the inverse of a square. And when we square things, it always turns positive. You'll never get a negative. So it wouldn't make sense to reverse that by inputting a negative into a square root. So another way to think of that then is that whenever you see a square root symbol in an equation, whatever's underneath that square root has to be 0 or bigger. It can't be negative. We have to force it to be 0 or bigger, or we're going to end up with issues when we try to take the square root. Okay, the rational function, that's the one that is essentially a division problem. The rational function has a restriction because we can't divide by 0. So when you see a function that has division in it, we need to make sure that that denominator does not equal 0, or we're going to run into trouble when we try to divide. And then the logarithmic function, we really want to think about how logs are the inverse of the exponential. So picture that exponential growth or decay graph. When we think about exponentials, exponentials can input anything, but they only have positive outputs. So if exponentials only have positive outputs, then the inverse, the log, can only have a positive input. So when we see a log function right here, we need to make sure that whatever is in the input of the log is in fact positive. We have to make sure that it's greater than 0. If there was a negative number inside there, then we're going to run into issues when we try to take the log. For the next part of this video right here, we're going to be exploring some specific functions that are not the parent functions anymore. You'll notice that we see, for example, a quadratic function, a rational function, an exponential function, but now we don't just simply have x right here. We have a variation of that function, and you'll notice that all of these have 2x minus 3's in them instead. So there's been some transformations done to these parent functions. We'll visit transformations a little more in these upcoming weeks. Hey, but for right now, all I'd like you to do is take a look at all the functions in this box right here and circle or highlight the functions that do not have unrestricted domains. Okay, and actually I give you a little hint at the top here. All but 3 of them have unrestricted domains. Your job is to try to find the 3 that have restrictions. Okay, once you've identified them, then use the space below here to try to actually find the domain of those 3 functions. The other ones all have domain all reals, but 3 of the ones in this box have restrictions on the domain. So take a few minutes here, pause the video, see if you can first identify the 3 functions and then actually go find the domain of those functions. And when you're ready for either feedback or more guidance, then you can go ahead and restart this video. The rest of this video will take a closer look at the 3 functions that you hopefully identified in the box, and then work to think about what the domain would actually be for that function if it's not all reals. So the first function that you hopefully identified is the square root function. So let's take a look here. The square root function we decided above has an restriction on the domain because we cannot take the square root of negative numbers. So when we look at this right here, we need to look at what's underneath the square root and say, all right, I can't let that be negative. I need to make sure that whatever is under that square root sign is 0 or bigger. And so we can do that by actually taking what's under the square root sign and using an inequality to force it to be 0 or bigger. So I'm setting up the statement right here that 2x minus 3 has to be greater than or equal to 0, because if it's not, we're not going to be able to take the square root. And now I have a little equation that I can solve, or a little inequality. I can add 3 to both sides to undo the subtraction, and then I can divide both sides by 2 to undo the multiplication, and I end up with this result that x itself must be greater than or equal to 3/2. In other words, x itself better be 1.5 or bigger. If I try to plug something smaller than 1.5 in for that x, I'm going to end up square rooting a negative, which is something we just can't do. So here's how we could state the domain. There's really 3 ways you could do it. You could say it in words. We can say that the x values in this equation must be greater than or equal to 3/2. We can use an inequality symbol to say that, which is basically what we got when we solved this inequality. X itself must be greater than or equal to 3/2. Or we could use interval notation, which says that 3/2 is the smallest number we can plug in for x, but we can plug in numbers anything larger than that. We can go to the right forever. And if we were to graph this, we would see a graph that starts at 1.5 on the x-axis and then goes forever to the right. Okay, the second equation that hopefully you identified is the log graph. Okay, the log function is actually a lot like the square root function in that we can't take the log of negatives. Okay, the difference here, though, is we also can't take the log of 0. And again, this gets back to the fact that exponential functions only have positive outputs, so log functions can only have positive inputs. So the work we're going to do here is almost exactly the same as what we just did for the square root function. The only difference is we're not including 0 this time. Because while we can square root 0, we can't take the log of 0. So we strictly want that 2x minus 3 that's there to be bigger than 0. We need it to be positive. And now I have a little equation, actually inequality, that I can solve. I can add 3 to both sides, making this 3 over here. I can divide both sides by 2, and I'm left with the result that x itself must be something bigger than 3/2. Or in other words, x must be bigger than 1.5. And so again, we can express the domain 3 ways. We can say it in words. The x values must be greater than 3/2. We can use an inequality, x is greater than 3/2. Or we can use interval notation, which says that x can be any number on the number line as long as it's bigger than 3/2 but smaller than infinity. Somewhere between 1.5 and infinity. And then last but not least, the one other function that we have to think about restrictions on is the rational function. So the rational function is this one at the top here that involves division. And once again, this one has a restriction because we cannot divide by 0. So I'm going to look at this equation and I'm going to look at the denominator and say I see a 2x minus 3, and I need to make sure that that does not have a value of 0. 2x minus 3 cannot be 0 or I'm not going to be able to perform the division. And then just like in all the others, I can solve this inequality statement. I can add 3 to both sides. I can divide both sides by 2. And in this one, I get the situation that x can be anything but 3/2. It can be bigger than 3/2. It can be smaller than 3/2. It just can't be 3/2 or 1.5 itself. So again, we can express that one of 3 ways. We can say it in words. X can be anything but 3/2. We can use the not equal to symbol and say x cannot be 3/2, implying that it can be anything else. This last notation is probably the most descriptive at all. It essentially paints a picture of the x-axis, and it says that we can be in the interval that's to the left of 3/2. We can be somewhere between negative infinity and 3/2, but notice the soft bracket makes it so that we don't actually hit or include the 3/2. And we can also be on the right side of 3/2. So we can be in that interval that goes from 3/2 to infinity. It's almost kind of 2 separate mini domains that are united, and this is a symbol called union, that are united to form the domain of the entire function. So x can be to the left of 3/2, it can be to the right of 3/2, it just can't be 3/2 itself, and we're communicating that with that soft bracket, once again showing that we never actually hit the 3/2. The rest of this document will give you a chance to apply what you've learned these last couple of days. So the rest of this work is yours to try. As we look here, you'll get a little practice finding the domain by looking at an equation. This one right here is a little bit of a challenge. See if you're up for it. Give it a try. Come with questions to our next meeting. You'll have a little bit of a chance to practice what we did yesterday, where you find the domain from the graph itself. Really pay attention to things like the open and closed circles to think about, do we actually hit that x value or just approach it? The next part right here will give you a chance, given the domain and range, can you draw a picture of what that graph could possibly look like? We did a little of that in the Desmos activity yesterday, so look back there for guidance if you need to. And then last but not least, for a little challenge, if I were to give you the domain of a function, could you come up with a possible equation that would have that domain? And it might help if you look back at the examples that we just did right here and to try to reverse your thinking. Given a domain, can you envision what the equation must have looked like that would have produced that domain in the first place?